There are certain standard sets of numbers that we use when we want to describe what sorts of numbers make sense in some setting. There are other sets of numbers that we could refer to, but these are the ones that we're going to use most frequently in this class. We have the natural numbers, sometimes called the counting numbers. These are just the numbers 1, 2, 3, 4, 5, and so on. When we type the symbol for the natural numbers, it looks like this. When we write it by hand, typically we'll just use 2 vertical lines for the left side of the letter N. This style of text is called blackboard caps. The next set of numbers we're interested in are the integers. For that, we use the symbol Z, presumably because integer starts with a Z. Well, at any rate, the symbol, again, is this blackboard caps letter Z. When we write it by hand, this time we'll have 2 parallel lines for the diagonal stroke of the Z. The next set we're interested in are the rational numbers. For those, we use the symbol Q for quotient. Right? These are the numbers that can be expressed as fractions. The symbol, again, this blackboard caps. When we write it by hand, we just use a vertical stroke here. And finally, the real numbers. How do we get the real numbers? We can think of taking the rational numbers and just filling in all the gaps between them. Are there really gaps between the rational numbers? There are, but the reasons why are outside the scope of this course. Well, it depends on what we mean by gaps also. When we write the symbol for the real numbers by hand, again, we just double that vertical stroke. When we're talking about the natural numbers, instead of saying the natural numbers, we'll sometimes say the positive integers. We might also refer to the non-negative integers to mean the natural numbers and also 0. Now notice when we have a rational number, it can be written in many forms. So 3/5 is the same as 6/10, is the same as -9, -15. Even though those all look different, they all represent the same rational number. That is, the same object that is an element of the set of rational numbers. This also helps us notice that we can't necessarily depend on what a number looks like to determine which of our number sets it belongs to. So if we have the number 6 and we want to say which of our number sets does it belong to, well, 6 is a natural number, right? It's a counting number, 1, 2, 3, 4, 5, 6. And then every natural number is also an integer. Right? The integers are the natural numbers and 0 and the negative versions. Can it be written as a fraction? Well, yeah, 6 is 6/1. So 6 is rational. And then every rational number is also a real number. Right? So think of the real numbers as just filling out the number line. Okay, what about -16/4? Well, that's not a natural number because it's negative. Is it an integer? Well, if we think of this fraction bar as indicating division, right? This is 16 divided by 4 and then make it negative. So -16/4, yeah, that's an integer, right? That represents the integer -4. Is it rational? Well, yeah, it's already written as a fraction. It's definitely rational. And then every rational number is also a real number. What about 3/5? Right? Is that a natural number? Is that an integer? It's positive. So if it's an integer, it's also going to be a natural number. But we notice that 0, right, that's 0/5. And 1, that's 5/5. And so 3/5 is between 0 and 1. So 3/5 can't be an integer, which means that it's also not a natural number. It's already written as a fraction, so yes, that is rational. And then every rational number is a real number. What about negative 7.78? Right? The decimals make it easier to see that this is not an integer or a natural number. Is it rational? It doesn't look like a fraction, but negative 0.78 can be written as a fraction where the denominator is 100. There's 2 digits after the decimal point, so I've got 2 zeros in the denominator. And then the numerator is 78. It's just what I see without the decimal point. So I can write that decimal as a fraction. It is a rational number, and then also a real number. What about 0.3 repeating? Right, that bar over the 3 means that the 3 just keeps repeating forever. Again, the decimal makes it easy to see that it's not an integer and not a natural number. Seeing that we can write this as a fraction is a little bit less obvious, but you might have memorized at some point as a fact that 0.3 repeating is equal to 1/3. And so this is rational, and this is real. Okay, what about the square root of 2? It turns out that there is actually no way that we can write the square root of 2 as a fraction. We'll see why in a little while. So the square root of 2 is not rational, it's not an integer, it's not a natural number. But the square root of 2 is one of these numbers that we fill in when we fill out the real number line. So we can understand the square root of 2 as a distance, as a point on the real number line. We can understand it geometrically. So that is a real number, even though it's not rational. Okay, so at this moment, you had to take my word for it that negative 0.78 and 0.3 repeating were rational, but the square root of 2 was not. How can we recognize rational numbers? Well, of course, all integers are also going to be rational numbers. If we have a number that's already written as a fraction, then that's also certainly going to be rational. What if we have a decimal? Well, if we have a decimal that is either terminating, so it stops after a certain number of digits, or repeating, so it has some pattern that repeats infinitely after a certain number of digits, then that decimal is rational. That decimal represents a rational number. Every other decimal is irrational. So if it keeps going forever without repeating a pattern, that decimal represents an irrational number. Another place we can look for irrational numbers is the square roots of positive integers. Now, sometimes we'll take a square root and we'll get another integer. But if we don't, if we take a square root and it's between two whole numbers, then that square root is an irrational number.